Hello everyone, today I would like to present a digital innovation that brings two simplistic but highly critical fields, biological calculus and national food security. Under Malaysian National Agro-Food Policy 221 and 213 NAP 2.0, our country is heavily committed to increasing our rice self-sufficiency level (SSL). To achieve the goal, we can no longer rely on traditional pest-based agriculture method. We need precision agriculture. This is exactly why we developed the paddy bioderivative analyzer. This application method, paddy biomass grow using advanced mathematical formula and calculus to determine the absolute best timing for fertilizer application and irrigation. What is the single biggest challenge faced by our rice farmers? It is known when the paddy crop is at its most critical growth is to absorb nutrients efficiently. If fertilizer is applied too early, the nitrogen leach into the soil and is waste. If applied too late, the crop yield potential drops significantly. This is where calculus play a central role. We often ask, where is calculus actually applied in the real world? The answer lies in the rice field. Our model utilizes a logistic growth curve, sigmoid. Now you can see the mathematical model. The first, cumulative biomass. A logistic growth sigmoid curve modeling total dry matter accumulate up to 420 days after transplanting date. Now you can see L is a biomass or max biomass per gram, and K is grow rate curve, and DO is reflection or depth. Now you can see the first derivative give us the crop grow rates, CGR. CGR tells us exactly how fast the paddy is accumulating physical mass on any given day. Even more fascinating, our application calculates the second derivative to measure growth acceleration. If the second derivative is positive, it means the paddy growth rate is actively speeding up. If it's negative, it means growth is slowing down to devote energy toward productive pace, the formation of rice grains. When the second derivative equals 0, the paddy plant has officially reached its maximum biological span limit. Now you can see the graph, biomass growth versus rate of change. Now you can see day 0 transplant. You can see at the dynamic agronomy diagnostic panel, at the day 0, you can see cumulative biomass or dry matter is 9.80 grams, and group grow rate derivative is 0.78. And then go the day 14. You can see at the day 14 is active tailoring. You can see dynamic agronomy is cumulative biomass is 188.51 and group grow rate is 12.71. And then day 16, you can see cumulative biomass is 576.01 and group growth rate is 23.69. 96. I'm sorry, 96. And then at the 85 day, you can see cumulative biomass is 1056.96 per gram and group growth rate is 10.09 per gram. And last day is day 120 is after transplanting or harvest. You can see cumulative biomass is 1190.20 and group grow rate is 0.79. And In conclusion, the PEDI bioderivative analyzer proved that mathematics and calculus are not merely abstract theory confined to a classroom blackboard. They are powerful tools that, when integrated into agriculture technology, can save farmers 20% to 30% in fertilizer cost through high precision timing, minimize environmental pollution caused by excess agriculture runoff, directly support Malaysian food security objective under NAP 2.0, which feature integration of satellite data and IoT field sensor. This assets calculus model can power the next generation of smart farming.
Good afternoon, everyone, and thank you for joining. Today, I am excited to share my research project, which bridges traditional Malaysian food processing with advanced bioprocess engineering. Well, my name is Daneshwari Chandramogan. I am from SFP course, and my matric number is F25A1803. Now, we are looking at solid-state fermentation in tempeh production, specifically tracking the growth kinetic of the mold Rhizobus oligosporus. My goal is to show how we can use calculus, specifically the first and second derivative, to transform a traditional rule of thumb bracket process into high predictable automated industrial operation. When growing Rhizobus oligosporus mold on soybeans, the fungus releases massive amount of metabolic heat. If the core temperature spikes past 38 Celsius, the batch spoils. Traditionally, operators just fill the packages with their hand. To scale this up commercially, we need automated climate control driven by mathematics. To do this, we use the logistic growth model. We kept the maximum growth at 12.0 gram based on Mardi standard. By taking the first derivative, we get the instantaneous growth velocity, which directly mirrors metabolic heat generation. By finding the inflection point where the second derivative equals 0, we identify the exact hour when the mold reached half its capacity and the heat generation peaks. Knowing this exact peak allows factory automation system to execute preemptive strikes. Instead of waiting for the soil to overheat, automated script trigger forced air cooling system at the precise hour of maximum heat flux, keeping the batch safe.
Hi everyone, my name is Zina Sharmisan with your SFP. My matric number is F25A1902 from SFM. Today I will be presenting my HTML website cited Bioscience problem. The Bioscience problem I choose is the challenge of all palm oil in Malaysia. To ensure food security without clearing new forests, we need to maximize FFB yield from existing trees. The problem is all palm yield follow a biological cycle. It starts low, increase rapidly at maturity, then decrease again as the tree gets taller and older, making harvesting difficult. Therefore, agronomists use this derivative to calculate the exact time when yield starts to decline. This is important for planning the most efficient replanting cycle. Important of study this bioscience problem. It is important for us to study this problem because of three main reasons. Firstly, it has a direct impact on human health and food security. Secondly, if not addressed early, treatment costs and economic loss will increase. And lastly, is bioscience research help us find sensible solutions such as new technology or better policies for the future. This is my website. I click on the first point. The first point is the bioscience problem. Here I explain the problem of oil palm oil following a biological cycle. It increases then decreases when the tree gets old, making it hard and harvest. Secondly is application of derivatives. These sections show how the derivatives are used to calculate the field yield point and when the decline phase begins. This helps agronomists determine the most efficient replanting time. And the last point is graph of conclusion. Here I put a graph to visually prove how mathematics can help solve real agriculture problems. One way to improve this website is by editing CSS styling plus responsive design. Right now, my HTML is still basic with text only. If I add CSS, I can make the layout matter. Use Bioscience theme colors like green or blue. And make sure the website auto-adjusts nicely when open on a phone. This will make the presentation look more professional and user-friendly. That is all from me. Thank you.
Hi everyone, my name is Nura Hayati binti Mahdi. My matric code is F25A1829. Today I will present my project entitled Padi Kinetics and Mathematical Derivative, which focus on food security in Malaysia. Malaysia's rice self-sufficiency level is only around 65 to 70%, so the country still relies on imported rice. This project studies the growth of padi MR297 using mathematical models to help farmers improve rice production and crop management. This topic is important because rice is the main food source for Malaysians. By studying padi growth, farmers can increase crop yield, reduce fertilizer waste, improve farming efficiency, strengthen food security in Malaysia. Case study. This project focuses on padi MR297, a rice variety developed by Mardi. The growth of the plant is represented by F for X, while the growth rate is represented by F prime of X. Mathematical model. The logistic growth model predict the height of the padi plant over time. The first derivative measures how fast the plant grows on a specific day. Environmental factors. Users can adjust maximum plant height, growth coefficients, day of faster growth. These factors simulate different environmental conditions. Growth graph. The graph shows f of x is plant height, f prime of x is growth rate. The highest point of the derivative curve occurs around day 15, which is the fastest growth state. Kinetic calculator. At day 50, height is 52.50 cm, growth rate is 2.10 cm per day, state is penetration phase. Meaning of the derivative. The derivative tells us how fast the plant grows. At day 15, the growth rate reaches its maximum value of 2.10 cm per day. This is the best time for farmers to apply fertilizer and monitor the crop carefully. Scientific reference. The project used real data from Mardi crop manual, MADA irrigation reports. This makes the model more reliable and realistic. Recommendation. I recommended adding a fertilizer recommendation feature that suggests the best fertilizer schedule based on the growth stage. In conclusion, this project shows how mathematics and biology can be combined to improve rice production. By using derivative and growth models, farmers can make better decisions and help improve Malaysia's food security.